Welcome. Today is Tuesday, February the 9th at AP Chemistry here at Spain Park. Today we want to talk about reaction mechanisms. Okay, it's the last thing. It's the individual steps of a reaction. A reaction mechanisms. It's a series of what we call elementary steps. That describe how a reaction may occur. Not how it definitely occurs, but how it possibly could occur. Okay? And we're going to talk about criteria of what makes a mechanism valid or not, on whether or not it's a possibility. But the first thing we need to do is define, well, what is an elementary step? An elementary step is a single reaction that occurs exactly as written. In a single step. It's a little redundant, but making a point. So if I'm looking at just an ordinary reaction, we write a chemical reaction, hydrogen plus oxygen yields water. We cannot assume that that is all just one step, that one hydrogen combines with one oxygen and then all of a sudden water is made. Okay? Most reactions go through a series of different steps that have to occur. The hydrogens have to break apart, the oxygens have to break apart, rearrange, then the hydrogens and the oxygens come together to make the water. Okay? But when we have a mechanism, the elementary step, it's what I call WYSIWYG. What you see is what you get. WYSIWYG. Now, that term comes from way back. This is how old I am. When I first started teaching in 1982, we didn't have laptops, we didn't have computers. There wasn't a desktop computer. They had the big IBM super, computers that took up a whole room, but they did not have a desktop. But somewhere in the mid to late 80s, Apple came out with the Apple IIe, the different Apple computers, Macintosh, and I had an Apple IIe, and I was really excited. But then when you would type a letter or something on it and then go to print it out on your dot matrix printer, okay, with the dot matrix printer, it was the ones that had a wheel and it had the gears and the paper would feed through and it sounded like a typewriter. Anyway, they were super slow. Whatever I printed, had typed on the display, didn't always come out on the printer the same way. So you'd have to adjust the margins and all that. But then a few years later, they came out with WYSIWYG. What you see on your display is what comes out on the printer. That was huge. Now that's the way it is nowadays. Okay, but that was the next step in the development of the computer. Was what you see is what you get. So I say all of that to say, an elementary step is what you see is what you get. With most chemical reactions, it's not that. With most chemical reactions, they just give you the end result, but they don't show you what's happening in the middle. An elementary step is what's happening in the middle. What you see is what you get. Those are, and so every step of a mechanism is going to be an elementary step. Now, in an elementary step, I don't like that marker. Because it's what you see is what you get, in elementary steps, the coefficients are the exponents in the rate law. Now, the slowest step in the mechanism is called, what do you think it's going to be called? Anybody know? The slow step, yeah, okay? But it's called well, let's say the rate determining step. So, by definition, what do you think the rate determining step is? The step that determines the rate, okay? Very deep right there. The step that determines the rate. Now, have y'all ever, as a family or whatever, gonna go out to dinner, and everybody's ready, but there's always that one person in the family that just, I can't find my shoe, or wait, I gotta go brush my teeth. Just something, and you're always waiting on that one person to do something, and they're the reason. Everybody else is ready. That person's the one that's gonna cause you to be late. That's the slow step. That's the rate determining step. Or we could have 3 Usain Bolts running the legs, first 3 legs of a 4x400 relay, but if I'm number 4, we're gonna lose, okay? That's why I have that shirt, as if I ever had to run for my life, I would probably die. You know, it's just, you know, I'm gonna be the rate determining step, the slow step. So in the lab that we just did, the first reaction, the one we measured, was the slow one. But as soon as that iodine got made, the thiosulfate was sitting right there ready to consume it quickly before the starch could get to it. And so we had a slow one and we had a fast one. Now that was 2 separate reactions. It wasn't really a mechanism like that, but it still kind of shows us that some things go fast, some things go slow. So the slow step is the rate determining step, okay? So, and I'm gonna always abbreviate that RDS. And just because that way we don't have to write it all out every time, it's just easier. Okay, so there are 2 criteria for a mechanism to be valid. Number 1, all the elementary steps must add up to the overall equation. I'll give you an example of that in here in a second. Okay, and then number 2, and we call this the stoichiometry. This is just like Hess's law. Just like Hess's law, the 3 equations for Hess's law had to add up to the overall equation. When we have these series of elementary steps saying the mechanism, they have to end up being the overall reaction we're trying to describe what's going on. Okay? This one, that step's pretty easy. Then the second one is the rate law of the RDS, the rate determining step, must be the same as the experimentally determined rate law. The experimentally determined rate law, that's what we do with the differential rate law, where we go and we have, you know, X and Y rate equals, you know, whatever. So we figure that out first. The mechanism, the rate law of the rate determining step has to do that. And we can use the coefficients in that rate determining step to determine whether or not, you know, what the exponents are. So the exponents in this have to match what we figured before. Okay? Now, as an example of that, let's look at year 2000 Form A. This is the one that has that D on it that you didn't know how to do, that we're gonna now know how to do. have all this copied. Okay, there are two criteria. So we went through here, and we did this one already, okay? And we determined that the rate is equal to K times O3 times NO. Do you remember what was the name of O3? Ozone, okay, good. Okay, this is my experimentally determined rate law. This is my experimental data here. Okay, so whenever we're using this, that means that that's my experimentally determined rate law, because I'm using experimental data, I'm figuring that out. Okay, so now I look here and it says the following three-step mechanism are proposed for the reaction above, and the reaction above is given at the top, O3 plus NO. Do you guys have that? What's it make?
O2
and O2 plus NO2. So the first thing that we have to do here is we have to say, okay, and it's not saying is this valid, not to answer the question, but for a mechanism to be valid, if this is a valid mechanism of that reaction, these three have to add up to that. So I have O3 plus NO goes to O here. Now notice this O and this O. The oxygen gets created and then it gets used up right again. It's not a reactant and it ends up not being a product. When you have a substance that is formed in the middle of the reaction, it's called an intermediate. A substance that is neither a reactant nor a product it is formed and consumed in the middle of the reaction. Okay, so the oxygen, this is an intermediate. Are there any other intermediates? The NO3 is also an intermediate. Okay? It's formed in the middle, but yet then consumed. It's neither a reactant nor a product. Okay? Now, if I go through and just kind of want to do this, we can see the oxygens are going to cancel out, the NO3s are going to cancel out. We're going to end up with two O3s plus two NOs goes to two NO2s plus two O2s. You just take all your 2's out because it's 2, 2, 2, 2, and you end up getting the overall equation. Okay? So the first stoichiometry is these three add up. Now this question says, identify the step that must be the slow step in order for this mechanism to be consistent with the rate law derived in part D. Well, this is the rate law derived in part D. So when I'm looking at these three equations, you always assume in a mechanism each step is an elementary step. In other words, this is combining with this to make this directly. Okay, so in other words, the NO is pulling one of the oxygens off of here. Okay, or actually two of the oxygens off and leaving one. Then this combines here, and I mean, it's just what you see is what you get. That's actually what's happening on each one of these. So I can say that the rate of this one is going to equal K times O3 times NO. And the coefficients are both ones, so it's just to the first power. Now, that happens to be exactly the same as this one. That's going to tell me that this must be my rate determining step, because if this is a valid mechanism, the rate determining step, the rate law of the rate determining step has to equal the experimentally determined rate law. In an elementary step, we get to use the coefficients as the exponents. Okay? So, just for proof here, this one, what's the rate going to equal? O times O3. Both to the first, but this one is not the same as that one. So this can't be the rate determining or the slow step. And this one's going to be rate is equal to K times NO3 times NO. Okay, and again, it's not the same, so it's not the rate determining step. The one that has the exact same rate law is the one that's going to be your slow step. So you can go both ways. If they give you the slow step, then we know that whatever the coefficients are on that one, that's got to be my experimentally determined rate law as well, for it to be a valid mechanism. Okay? Now, if we look at one in your book on page 625, look at this one. Now, ozone in the upper atmosphere can be destroyed by the following two-step mechanism. Now, I did share yesterday, talk about this. Back in the late 70s, early 80s, okay, there was supposedly this hole in the ozone forming over Antarctica. And the ozone in the upper atmosphere is what blocks the UV radiation coming in. It kind of protects the Earth from a lot of the sun's harmful rays. Okay, so the ozone layer is very important. So it turns out that this chlorine, and it came from this chlorofluorocarbon, which we called Freon, which is used in car air conditioners and home air conditioners. When we used to work on, I had an old Chrysler, I mean, I bought it new, but it was a piece of crap, and the air conditioner would end up leaking. And I'm in Baton Rouge and it's hot, and so I could go to the auto parts store and I could go get a can of Freon, and I could just keep adding Freon to my air conditioner system, and then it would slowly leak out, and I keep adding. So all that Freon is going up into the atmosphere. If somebody changed the air conditioner system, they would just let it drain out and then take all the parts out and put the new parts in and then put new Freon in. Well, it turns out that this is a very stable molecule. Here down on Earth, on the ground, it stayed all together, but as it floated up into the upper atmosphere, then the UV rays got stronger and stronger, and it would knock and make what we call the free radical, just an unbonded chlorine atom. That chlorine would bond with the ozone, forming all this, and ultimately changing the ozone to oxygen gas. Now, oxygen is not poisonous, but it's depleting the ozone. Now notice also that the chlorine is getting regenerated. It found out that up to one chlorine could destroy up to 20,000 ozone molecules before it itself got combined with another chlorine to make chlorine gas, which, wouldn't cause the problem. It's a chain terminating step. So they banned these CFCs. They changed to more environmentally friendly, and the average Joe like me cannot go into an auto parts store and get Freon anymore. Anybody that does air conditioner work, has to have a Freon capturing system to collect the Freon and recycle it rather than just let it go off into the atmosphere. So this is all part of that reaction right there, okay? Now, all of that is just free. It's a freebie on a Tuesday. That's just general knowledge for you, a little history and science, kind of all going together. on global warming. So, is chlorine an intermediate? No, right? Is it going to be my overall reaction? Because it's going to cancel out, right? What do you think chlorine is? Say what? A catalyst. Okay? So this is going to be my catalyst. When you have a reactant that ends up being reformed as a product, and so it cancels out, that's going to be a catalyst. So you have to be able to differentiate between when it's an intermediate and when it's a catalyst. A catalyst is at the beginning and the end, an intermediate is in the middle. Okay? Now the catalyst is not just a reactant, it has to be reformed at the end, because the whole point of a catalyst is it speeds up a reaction without changing itself. Okay? So, what's the overall equation for this process? Well, we're going to cancel those out. We're going to cancel the CL. What is CLO? That's an intermediate. Okay? So my overall equation is going to be O3 plus O is going to go to 2O2. Okay, so that's just the stoichiometry. So I mean, most of the time they say, what's the rate law going to be of this? We just got to make sure this adds up to that. But in this case, they're saying, okay, if this is the mechanism, what's the overall? There must be this reaction. But again, note that this is the catalyst. This is your intermediate. Now, what is the catalyst in the reaction? What's the intermediate? We just did that. Now, we don't have anything, we don't know what the experimentally determined rate law is here, so there's no way for us to identify which one's the slow step on this particular one. Okay? Let's see if we can find one more. Okay, so we have this mechanism. Okay, so notice it's the reaction of NO with H2 going to form N2O and H2O. So what do I need? I need 2 here, right? So this is my overall equation. So the first thing that we have to do is say, does these two add up to this one? Well, yes. What's my intermediate going to be? N2O2. That's my intermediate. Is there a catalyst in this one? No. Okay? So let's see what the rest of the question asks for. Okay, so show that the elementary steps provoke. Okay, so we just did that. We added this up to here. Then it says, what's the rate law going to be? What's the rate law going to be for this one? Rate's going to equal, huh? No, oh, yeah, we did, sorry. But it's going to be on the previous one. You had your books
Write it
open.
off to the side.
Yeah, we have to write these off to the side here. So we have NO plus NO goes to N2O2. Then the other one is N2O2 plus H2 goes to, there's only one arrow, N2O plus H2O. So, what's the rate law? What's the rate law going to be for this one? Rate is going to equal K times NO, because it's really 2 squared. NO times NO, which is going to be NO squared. What's the rate law of this one going to be?
K N2O2
Okay? Now, right here, we have a problem. We generally don't include an intermediate in the rate law. Okay, and that's gonna be the last thing we're gonna talk about, how we can figure out ways to eliminate that. But here, so now we go back to what the question asks. Okay? Here we go, one more. Keep going, there we go. Now, oh, it is a fast equilibrium? No? Okay, observe rate law. If the proposed mechanism is correct, what can we conclude about the relative speeds of the first and second reactions? Well, we don't know that answer yet. I'm about to show you that answer. Okay? But, what are we gonna have, if this is the observed rate law, how's the only way we're gonna get to that? Somehow or other, this is gonna have to get substituted into there, right? This is gonna have to get substituted into there. All right, so let's talk about how we can do that. We're not gonna use this one as an example. But if most of the time, they'll give you the experimentally determined rate law, and it'll just match up directly to one of these. And that's how I predict what the slow one is. All right, so let's go back and look at your 19 on the packet. 1991. Okay. We haven't done any of this one, right? So go through right now and determine what's the experimentally determined rate law. Part A, write the rate law for the expression. And this is a good one because, good practice, because this doesn't change. I mean, it does stay constant. know what you're doing, you got it. If you don't know what you're doing, we'll be here all day. So, somebody tell me, how do I do this one? How do I start? Anybody have an idea? Did we get values for X and Y? How'd you get it, Adonai?
For F2, I saw the 0.01 constant on the CO2
So this one is,
times 4,
and this one is
rate is
times 4.
times 4. So 4 to the X equals 4, so X is 1.
So 4 is equal to 4 to the X. X equals 1, so it's first order with respect to fluorine. Okay, so what do I do now? Because none of these stay constant.
I mean, I just saw the coefficient.
Okay, but we have to be able to show the work. We have to be able to prove it.
Okay, maybe
What if we go here to here,
that's times 2,
and here to here,
times 2,
times 2, here to here,
times 4.
times 4. Okay, so we're going to say the rate 4 is equal to 2 to the first times 2 to the y. Because we now know that fluorine is to the first, so it's no longer a variable. You just have to include the one that you just figured out in the second rate law to try to figure out what the second one is, because they're both affecting the rate. But we know that the effect by the fluorine is first order. So we can then say 2 is equal to 2 to the y, so obviously y equals 1 as well. So my experimentally determined rate law is rate is equal to K times F2 times ClO2. Okay? Then we just go and find the value of K. All right, we can plug it in. Rate is 2.4 times 10 to the minus third molarity per second is equal to K times F2, 0.010 times 0.1. So K is going to equal
2.4 liters per mole.
Is it just 2.4?
Yeah.
2.4. Now, this is molarity times molarity, so it's molarity squared, but one of them's going to cancel out. So it's per molarity times seconds. Or as Advite was going to say, molarity is moles per liter, so you can just invert and say liters per mole seconds. Either one of those is 100%. I think molarity is easier just to keep track of, but it's always just going to invert when you divide. Okay? So that's my K. Now, when you look at C, and I don't know, hopefully you guys all have your sheet out there, and you look at C, it says, in experiment 2, what is the initial rate of decrease of fluorine? The initial rate of decrease of fluorine. Well, what's the rate measured in? The increase of this, right? It's the question's asking for this one, the rate of decrease. Well, how is the rate of decrease going to compare to the rate of increase of this one? It's going to be half of it. This is the relative rate law question. Okay? It's very simple to do if you know what you're looking for. But we go through and try and do math on all of this one, but the reality is this rate is going to be twice as fast as that rate, or fluorine's is going to be half as fast as this one, just because of the 1-to-2 ratio. So the answer in experiment 2, what's the rate of decrease going to be for this one? Well, the rate of increase is 9.6, so the rate of decrease is going to be 4.8. Now, all that's review. So let's get to the fun part. Okay, so over here, just again, the rate of F2 is gonna equal 1/2 times 9 point, was it, 6? What,
Yeah.
times 10 to the minus third. So it's gonna equal 4.8, 10 to the minus third molarity per second. That's just, I mean, as far as the answer to C, just so you can have that. So now D. Which of the following is consistent with the rate law developed in A, and justify your choice? This is what we're gonna look at right here. What does the double arrow mean? Reversible or equilibrium. What's the definition of equilibrium? Okay, you gotta say it loud for me to hear.
It reacts as fast as they went.
The reaction is as fast
Everything is
in each direction, right? The rate of the forward reaction equals the rate of the reverse reaction. So at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. That's the definition of equilibrium. Okay, so this is going to be like a math substitution, but in order to be able to prove that this equals the overall rate law, so I know my rate law is equal to this. Well, if I wrote the rate law for my slow step, this should be my rate determining step. Well, then I'm going to say for step 2, the rate is going to equal K times ClO2 F2. Now that isn't anywhere close to this one. Okay? And it has an intermediate in the rate law, which we don't want. Okay? But seeing this, I know that I can say, but for step 1, the rate forward equals the rate reverse, which means that K forward times ClO2 times F2 is equal to the rate reverse, which is K reversed times ClO2 F2. Okay, anybody see where I'm going with this? Where am I going, Abby?
We're gonna substitute that into step.
Okay, so now just bring the K reversed over, so we get K forward divided by K reversed is times ClO2 times F2 is equal to the concentration of ClO2 F2. I'm just doing a proof. Now I can substitute into substituting into the rate law. Okay, I can say now that rate is equal to K times Kf over Kr times ClO2 F2, but a constant times a constant divided by a constant, just some new constant, right? If you're just multiplying and dividing constants, it's going to end up always being the same number if we use the same constant. So our final rate law is going to say rate is equal to K prime times ClO2 times F2. Okay? Which is the same as the experimentally determined rate law. So it's the same as the experimentally determined rate law. So the two match. So when we say write the justification then for this, well, what are the two criteria for a mechanism to be valid? They have to add up. Now this got cut off, so we're not going to kind of go and show the adding up. Okay, but these steps all have to add up to my overall equation. And the rate law, the rate determining step, has to equal the experimentally determined rate law. But when you have this fast equilibrium, you can do the substitution. Now I'm going to show you some ones out of the textbook. Your textbook doesn't have very many good ones. Take a break. No. Well, yeah, go ahead.